And so we're going to start chatting about the alchemical design framework in BCL. The alchemical design framework is named the alchemical design framework because it does not, or at least it was not originally intended to necessarily perturb molecules based on specific chemical reactions. This was sort of just I'm a human, I want to add a fluorine. I'm a human, I want to take my ring and change the carbon atoms into some heteroatom. You know, it was a very much just a way for people to explore structure-activity relations. And what I want to do is really sort of walk us through what the syntax is like in BCL and how that carries over to Rosetta. And so this one is actually going to be highly interactive. There is not a specific PowerPoint for this, and so please pay close attention. I was going to create a PowerPoint for this one, but then I sort of figured that showing you a bunch of pictures of molecules with different perturbations in them doesn't really add much beyond what the tutorials already show, which is how to access the help options to get to those types of perturbations. And then it walks you through some examples about what types of ways you might want to start thinking about designing the molecules and what types of tips and tricks we have. And so this is part one of this tutorial. And so tomorrow when we start up again, we're also going to be chatting about the alchemical framework. Thinking about, you know, now that you might have gotten your hands wet with feet wet, hands dirty, whatever, with these tutorials, then we're going to start integrating some of the sequence perturbation and design stuff of Rosetta and say, how can we really do some fun things with it? So, so this one's really fun. So we're going to start with the BCL syntax. Let me go ahead and share my screen. Okay. Yes, actually, before we start doing these, yeah, talk for tutorial 5 is really just good stuff. And so let's go to Eclipse. Actually, before we do that, the application we're going to use, I pointed it out earlier. It's called Molecule Mutate. Molecule Mutate is a base class or an interface class or some sort of mix of the two. It actually contains a bunch of member data, but it also has virtual functions that are defined by virtual void functions that are defined by these guys. And so when you want to perform a mutation, you have to tell the application what type of mutation you want to perform. And so this is sort of similar to the molecule split application, where the molecule split application will take a molecule, it'll specify an implementation for how do I want to split it, right? Do I want to split out rings? Do I want to split out rigid fragments? Do I want to split out something else? Also called implementation. Molecule mutate is the same. It says, okay, pass an implementation and tell me how I'm going to mutate. Am I going to add a bond? Am I going to add a medicinal chemistry functional group? Am I going to perform alchemy, which is where I directly just convert particular atoms into other particular atoms? Connect is an not yet ready for release one, but you know, it's for the developer community. You've got developer BCL, so you get to look at it. The Connect app is really meant to close disconnected fragments that are separated in space without perturbing those fragments. So useful for hopefully things like PROTACs or combining multiple inhibitors. Cyclize is a semi-finished, it works, but we're expanding the functionality. This takes a molecule and it creates an extra cyclization in it. This is going to be used for growing out of molecules. Extend with linker is a Swiss Army knife. It does a bunch of things that you'll experience in your tutorials. The general idea is maybe you have a scaffold molecule and you want to grow off of it or you want to grow within it. And there's lots of different ways you can do that. And so we'll take a look at that in more detail in a moment. Fluorinate and halogenate are two different mutates that we can use to modify molecules with halogens. You can, in fact, add fluorines with halogenate, but there are some special rules that are worth considering when we're doing these. And so because we tend to think about these things as chemists a little bit differently than some other atoms. And so it was worth making some special rules. React. And so you'll remember in my PowerPoint from the previous one, I showed you that React is part of the Alchemical framework because we've modified it to incorporate it into here. It cannot perform enumerative reactions. It can only return a single design in this framework, but it is nonetheless available if you want it. Yeah, remove atom, remove bond. Remove bond is a bit of a misnomer because remove bond and add bond are aliases for the same class, and they're really just a modify bond, really. We can also change bond orders and do some other fun stuff with these. And then the other app, or the other implementation, add medchem, I say is sort of a reaction-based one because in the tutorials, you're going to learn how you can actually use this to perform one-shot reactions without actually setting up a reaction file to make it easier. Because a lot of people encode their reactions not actually using a real reaction scheme, but just by taking, you know, some dummy atom in molecule A and some dummy atom in molecule B and saying, hey, I need to connect these two things like that. And so we can do that as a special use case of add medchem because that's sort of how the functionality works anyway. So yes, let's go ahead and get started looking at a few of these. Oh, sorry, before we do that, I did want to show you the code. And so this is Molecule Mutate. All of these classes derive from something that we call Fragment Mutate interface. And so Fragment Mutate interface in the BCL, this is something that you know, it derives from mutate interface. It's going to return certain things, blah, blah, blah. The idea is, though, that this is an interface class. And so if you have an idea for a new type of perturbation that you want to do to your chemical scaffold, we can potentially work it into this type of you know, code design scheme if it's something that's of interest. The other thing that's, so in other words, this is very modular. We can plug and play, we can add stuff and take it out pretty easily, which is kind of fun. It's a sandbox. The other thing that's worth mentioning, the mover that you're going to use in Rosetta is called Fragment Mutate Interface Mover. And so, as you might expect, you know, I guess it's Fragment Mutate Mover, but the idea is that in Rosetta, we can get access to all of these implementations and every implementation that anybody ever writes if we derive our, or not derive our mover, but create a mover in Rosetta. And so now we're actually looking at Rosetta code. This is no longer BCL code. And in Rosetta, we have our constructor for BCL Fragment Mutate Mover. And I've uncommented the ifdef just because it's easier to see. I have those blocked out if they're inactive usually. You see that as part of the constructor, we need to take a util implementation of BCL Fragment Mutate Interface. So the BCL util implementation essentially allows you to construct an object of type in this template. This is a templated argument, Fragment Mutate Interface, based purely on a string. And so you can pass essentially a string to the constructor. And if it's a string that can be read in much the same way these are read from the command line, then it can be initialized with the mover object. So really, all we then have to do is define a mover that does something with this object once it is constructed. And that's pretty much all we have here. And so when you get into the XML part of this tutorial, let's actually walk on over to that right now. We will look at this. This is one of our XMLs that you guys are going to be using. What you're going to find is you're making these BCL fragment mutate movers. You're specifying something simple like a ligand chain, like X, which is what we typically do for ligand docking. And then you're just passing this string. And what you may notice now that you've been using the BCL for a few days is that this looks a lot like BCL syntax. And that's because it is. This is the string that you will use to construct the BCL object that this Rosetta mover will use. And so you can specify whatever type of implementation you want right here. And it's going to be used to construct one of these suckers. And so we've got extend with linker, we've got add medchem, we've got halogenate, alchemy, ring swap. We've got all the stuff that we can do, and we can use it with any Rosetta XML script protocol. This is not just limited to Rosetta scripts. This tutorial and sort of how I do this is in Rosetta scripts mostly because I have a strong bias toward Rosetta scripts. I like it a lot. You can rapid prototype very rapidly. No redundancy intended. But I should say that you can do all of these things in PyRosetta. Sergey's been helping me with this. The idea right now is if it's a Rosetta object, so Fragment Mutate Mover is a Rosetta object, we can construct it for use in PyRosetta, and you can do whatever you want to do. I need to double check, since I haven't spent as much time with this, that you have access, you should have getters and setters for all the right options, so that way you can set these up, you can do things with them sort of dynamically in PyRosetta. And I should make sure that all the constructors are exactly how they need to be. But the main kind of point is that we can work with these things in PyRosetta or Rosetta scripts. And we're hopefully going to be extending the functionality so that way you can also have access to the lower level BCL objects with Python bindings as well. And so all of this is still in development, but it is progressing pretty quickly, and we're very excited about it. And so if there are modalities in which you want to work with this, Rosetta applications, PyRosetta, Rosetta scripts, whatever it is, or if you want to develop a protocol, we can chat about maybe what would be the best way to develop the protocol. But okay, so you will experience that. You will get to try out the XML scripts. I will also periodically have you doing commands for BCL throughout tutorial 5. But let's try a few of these. So, so let me show you my input molecules. Ligands. All right, these are scaffolds for, well, I have them labeled for DDR1 kinase, but really they're scaffolds for a lot of kinases. Very simple, 2 benzene rings connected by an amide. Excellent. We have this. We can label our atom indices. Let me set label size 25 so you can really see these things. So now we have our labels, so we can see where the atoms are thing. We can go ahead and change, let's change some elements. Let's change, atom index 0 to a nitrogen. Why not? Atom index 0. So we're going to do molecule, mutate, input file names. I'll make this bigger. We're going to do input ligands, SDF. We're going to pass our output blah.sdf. That's what we need. I hope Jeff Mendenhall's watching. Implementation. We're going to use alchemy as our implementation. Maybe we don't know anything about alchemy at the moment. So just like anything else, we can pass the help option to find out what the things are. Tutorial 5 is very long because I spend a lot of time discussing what are the different options, when might you want to use different options, what are some tips and tricks related to these options. And so especially when we're talking about how to control which atom indices we're going to be mutating. Because as you might imagine, it's really hard to decide which atoms you're going to change in part of a molecule you've already changed, in which you might not know what the new atoms are, let alone how they're ranked with respect to all the other atoms in your structure. And so tutorial 5 goes through that in quite a bit of detail. Tutorials 6 and 7 also expand upon that. So the next few tutorials really hit on this topic pretty hard. But one of the things we can do, well, so first off, I should say, if I just run alchemy without any other options, I don't know what it's going to do. It's going to change my molecule in some random way that I don't know. Let's find out what happened. It deleted it, which means what it effectively did is it took a carbon atom and turned it into a hydrogen atom. So that's not what we wanted to do. Let's put some constraints on what alchemy is allowed to do. I'm going to say allowed elements, nitrogen. I'm going to say mutable atoms. We'll say 0. So that doesn't mean there are no mutable atoms. That means index 0 is mutable, where we're 0 indexing. And I'm going to say, I think set formal charge has to be 0. I don't want it to add any charges. And let's try that. All right, and now let's actually just open up blah on top of this. All right. Now we have a new molecule. And this molecule just has a nitrogen substituted where that carbon used to be. Notice it removed the hydrogen atom as well, because if we were to have this, hydrogen atom here, this would be a +1 nitrogen. Actually, I don't even know if that is a resonance structure that is very stable. And so let's find out what would happen. So what this algorithm will actually do is try to figure out what is the most stable sort of atom type to replace that particular element with. And if it doesn't find anything that's possible, it won't do it. But if it does, it will replace it. So let's do open blah. And it says we can make a +1 nitrogen here, but we're going to remove that double bond. You're no longer going to have an aromatic system because this is a more stable atom type. And so now you have a nitrogen +1 in this ring. I could try to force it. I could try to change this bond type to force it, but usually we don't want to try to force those types of behaviors. Okay, so what else can we do? Let's try ring swap. And so ring swap was something that Jeff Mendenhall originally wrote. So the way that this sort of progressed was, let me actually just go back here and change the options out. I really wanted to start coding this, and the very first one that I programmed was Alchemy, with Jeff sort of teaching me and helping me along the way with how we manipulate some of these element types. And then we both kind of went nuts. So Jeff wrote one called ring swap. I wrote about 8 more that do different things like cyclization and extending the molecules and doing functional group modifications and doing halogenations, all kinds of stuff like that. And then Jeff and I always debated how we wanted this to behave. I really wanted a lot of customizability I wanted to be able to resign. And Jeff was always telling me, no, Ben, we should definitely let this do whatever it wants to do. So ring swap has some really intelligent independent sampling properties. But we've also added in as a compromise. I went back and edited things to allow it to be conservative in the types of rings that it will change with. So I don't know if Jeff's even listening to this particular talk, but that was a lot of fun to do these. I'm not going to worry too much about all these options. Let's just go ahead and say mutable atoms. We're going to say 4. It's still on this ring. Didn't get anything that could work. Must not have made a good conformer. Oh, there we go. Now we got something. And so you'll notice it tries, but if it doesn't find either a valid conformer or a valid swap, it's going to return null, and it's just going to essentially give you no output. And so it replaced my ring all right with this gigantic other ring. And that does not look like something we ever want to make. One way that we can prevent that from happening, well, there's lots of ways we can prevent that from happening. One of them is by specifying a ring library. So I can actually say, what are some approved rings that I would be interested in having swap out with my ring? Another thing that I could do would be to have a drug likeness filter. Be able to say, listen, you can make any swap you want, but you're going to have to pass a filter before you can move forward with it into the next part of the algorithm. Excuse me. We can also do conservative substitutions where we require that the ring is not too much larger than the previous ring or too much smaller. And we can realign those rings so that way they attach at the side of the molecule that preserves some aspect of bond mapping. And so I'm not going to go through that in too much detail right now because you're going to go through that in lots of detail by yourselves during your tutorials. But there's all kinds of ways that we can control the behavior of the ring swap. We've also got this really cool behavior where you can collapse rings. And so if you want to, you can take no atom and expand it into it, or one atom and expand it into a ring, or you can take a whole ring and collapse it down into nothing. And you can set the probabilities on that as well. So if you don't want it to happen, it doesn't have to happen. This time we've got a cyclohexane. Excellent. So anyway, let's go ahead and like I said, you can control this. You can specify benzene is the only ring you're ever allowed to swap in here if you want to. And you're going to do that, and I'll show you an example in a moment. But first, I want to show you. I don't know. Let's do a fancy example since we've only got maybe 5 more minutes left or something. With Fragment Mutate interface, you can chain these together. Where did I put it? And this is an optional example that's actually in the tutorial. I don't, keep it as part of the formal thing, but I wanted to show you an example. And let me take this apart piece by piece. So in here, you'll notice after my implementation flag, first I have an alchemy. And so in this alchemy, I'm saying, okay, take atom 13, which in this case is my, actually, I don't even remember what atom that is in this particular case. We're not going to worry too much about that. I think it's a carbon atom in one of my benzene rings. Take atom 13, also only replace it with a carbon, right? So the only element I'm allowed to potentially substitute it with is a carbon, but then restrict to bonded H. For certain reasons that you'll read about in the tutorial, you don't usually want to try to reference hydrogen atom indices directly, mostly because hydrogen atoms are not as well conserved with respect to their rank order in the molecule as other atoms. And so one of the options is let's specify a heavy atom and then say that I'm only actually allowed to select hydrogen atoms that are bonded to that particular atom. And I'm only allowed to mutate that to a C. So this effectively is going to convert a hydrogen atom into a carbon. Then I would like to add a medchem group onto that. Okay, well, what medchem group am I going to add? I happen to have this little library right here, and we're going to pull out an ethyl amide. And then I'm going to fluorinate it. And so at the end of this, we should get out a few different molecules. All right, so that is how fast it takes to run. So there's always like a 2 to 3 second, initiation period to load the rotamer library, after which it goes pretty quick. So our original scaffold was actually this benzene ring. Let me open it so you can see it. Original scaffold looks like this. So you're no carbon down here. Clearly these things are in different parts of space. That's not the one I designed on. Let me pull up. Which one did I design? Oh, this one probably. Yeah. All right. So as you can see, when we do these mutates as well, we preserve the coordinate space of our molecule. So we are not changing our molecule unless we absolutely have to get a valid conformer. So that's an important part of this interface. All right. So first we took our hydrogen and our starting molecule, we turned it into a carbon. The next thing we did is we grew an ethyl amide off of that. And then the third thing we did is we fluorinated it. And so what we ended up doing effectively is adding this sort of anchor into some lower portion of the molecule. This was done entirely in, by itself in a vacuum. There's no protein, there's no scoring. What actually happens when you do this in Rosetta, which is really kind of fun, this new part of the molecule that we grew. So this part, these atom indices are set to be those sample by parts atom indices that you read about in conformer generator. And so this means that the only atoms that are allowed to be sampled after we generate a new molecule are the new atoms. And the reason why is because we want to keep our molecule sort of locked in space, but then define new rotamers that Rosetta can sample during relax and minimization and repacking and all that other kind of stuff. I guess not minimization, but you know what I mean. That we want to allow Rosetta to sample. We don't want Rosetta to sample a global conformational ensemble, but we want to let it fix, the rotamer so that way it packs better in the protein. And so we try to impart flexibility only when we really need to. And so a lot of the tricks related to choosing which atoms are mutable, choosing which atoms contribute to flexibility are sort of derived from the parts of the molecule that are novel substructures as you progress. So So yeah, this is the general idea with this framework. When we start to get started on the tutorials, I think this should hopefully give you an idea, an introduction to it. There are a lot of details here. I've spent a little bit of time with some of you individually on this a while ago. Daniel Zeidman and I had some cool chats, and some of the folks in my office like Owen and Richard and Hannah. But for a lot of you, this is going to be a lot of detail. Please don't hesitate to ask questions about any of the functionality or how we're tracking atoms or any of those types of rules. There are lots of things that we're going to continue to do to expand the control over the atom selection and the flexibility, some of which I hint at in the tutorials. But the goal for this framework is really to create a level of customization in drug design, whether you're doing ligand-based or structure-based drug design, that sort of parallels the level of customization that you have for protein design in Rosetta, where you can do pretty much whatever you want. And so we're trying to really make a sandbox for small molecule drug design. So yeah, let me know how it goes. Later on, we will talk about using that add medchem mover, not just to append functional groups, but to actually do reactions. It's either in tutorial 5 or 7, but either way, tomorrow we're going to talk about it. So in the meantime, though, don't hesitate to reach out. So yeah, if you guys have any questions, I'm happy to take them. Otherwise, we can get started.